let's get started before the FBI come for me. Right, so in question 1, you are being asked to find the mean and standard deviation of a sampling distribution. Right. Now, it depends on which number you are given in the question. If they tell you P, the mean is P. And if they tell you, oh, that's a mess. If they tell you the sampling guy P hat, then the mean will be P hat. The standard error uses this formula. They're calling that guy the standard deviation. I wouldn't worry about it. It's the same formula, so it doesn't matter. So in question 1A, you are told N is 800 and you're told P. And so question A says, what is the sampling distribution mean? And the answer is, it's whatever that guy is, so it's 0.5. And then they ask you for, well, I wish they wouldn't keep changing its name. I'm calling it standard error, because sometimes they're calling it standard deviation, which it is, and sometimes they're calling it standard error, which it is. So the formula for calculating it is that guy. And I'm using P in my formula because they told me P. If this question had said P hat is 0.5, wouldn't I just say P hat 1 minus P hat over N, right? They're virtually interchangeable, right? So don't get too caught up on the P hat issue because the calculations are the same.
So that P times 1 minus P? Or?
Yeah, so P is 0.5. 1 minus P is what you do if you take 1 and subtract the value of P for it. And unfortunately, in this case, it happens to be the same answer. But I mean, if this is 0.7, that guy will be 0.3, right? And N is 800. And so I'll go to my calculator and I'll do the square root of 0.5 times 0.5 divided by 800. And the answer I get, which has to be rounded off to 4 decimal places, is 0.017. And that's 6 rounds up to a 7. And there's my answer. Okay. Pretty straightforward. The mean is that number. And the standard error or standard deviation, whichever name they want to call it at the time, is going to be this formula here. Oh. Now, question 2 is just like it. Let's move on to question 3 now, where they give you a kind of choice, right? Because they're telling you 2 different things. So, don't need that. In question 3A, a recent study has shown that 39.6% of Americans, well, I'm turning that into a decimal because we need to use decimals in the calculations. Right, so 39.6% of Americans are fat. They call it obese, but we're fat. A large medical clinic would like to estimate the percentage of these patients who are obese. So they take a random sample of 500 and they find out that from their 500, so I'll separate that, they got 170 out of 500, and that ends up being their answer. That's what they are. I'll find out what that is as a decimal. So that's 0.34. So that's the population number, right? It is known somehow or other, they did a census, and 0.396 of Americans are fat. And this sample, do you see it's a little bit different, right? 0.34, as you'd expect, right? Take a sample, you get a little bit more fat, sometimes you get a little bit less. This is a little bit less. So this is going to be a mixture of using P and using P hat, right? So
170, that's the number of obese?
Out of 500, yeah.
Okay.
And that ends up being as a decimal 0.34. And we're using decimals all the way through. So that's why I converted that straight into a decimal. Not a percentage, but a decimal, a proportion as we call it. Now question A says, population, proportion, P. Well, that question is so easy, you'd probably think and overthink it and write some down. Haven't they told you what the answer is right at the start? So you're just repeating yourself. Now, what is P hat? Oh, I've just found that a minute ago. So there we go. Question C says, what's the standard error of P hat? And then D says, well, let's do standard error first, right? We've got this fella. Now, I have two numbers I could be using, right? I could be using this one. I could be using this one, right? They asked me to find the standard error. So that means I'm using the one with the P in it. So it's P, 1 take away P over N. In this question, I'll need more than P, population value is 0.396. 1 minus P is 1 take away that number, which is 0.604. All divided by the sample size, which is 500. And then on my calculator, I'm going to do the square root of that times that divided by this. And the answer I got is 0.021876 and a whole load of stuff. And they want the answer to 4 decimal places. So 0, 2. I did some wrong there. Interesting. Let me try something here. I did. I know what I've done wrong. Does anybody know what I did wrong? Don't I have 2 formulas? Guess what I did wrong? I used that one, right, when I should have used that one. So, right, oopsie. Now, P hat is 0.34. 1 takeaway P hat is 0.66. That guy there is still 500. I thought I'd done that right as well, which is really annoying. 0.34 times 0.66 divided by 500. And I'm going to fix that in a minute, but 0.21184 and some stuff, that ends up being 0.211. Is it 3 places? 0.02112. There we go. We got it. Make that a little bit near. 0.0212 there. So let me get this fella sorted out. The guy they're calling standard error is this fella, and the guy they're calling standard deviation is the other one. And I wish they hadn't given them 2 names, because I call everybody standard error, and that's where my mistake was. So if they see standard error, use the p hat. If you see standard deviation, use the p. Are we good with that? Standard error, p hat. Standard deviation, p. So we then go on and we do question E then, which is the standard deviation, p hat, which means you use this fella. And that was the one that I rubbed out last time.
Oh, you already did D?
No, I'll go back. I skipped D. Let's do this guy. I had that answer. Whoops, I had that answer a minute ago. So let me see if I can bring it back up. No, of course I can't. 0.396 times 0.604 divided by 500. Okay, and that is 0.02187 and stuff. And to 4 decimal places, that's 0.0219. So the standard deviation uses P. The standard error uses P hat. Get that in my head. Standard deviation uses P. Standard error uses P hat. So hopefully I won't get them back in front next time. And you're right, I did miss D. And D is asking us for the mean of the sampling distribution. And the mean of that guy is 0.396. That guy. So P goes with P. P hat. Now it makes sense, doesn't it? P hat goes with P hat. P goes with P. Right. So population is a P. Standard deviation goes with population. Sample is a P hat. Standard error goes with P hat. Try to get these two in my mind together, right? With their names. Population P, standard deviation P hat. P hat, P hat. Are we good? Right. So we're really just going to get practice right now at calculating standard deviations or standard errors, depending on what information they give you. So if I tell you P is that and N is that, are you going to get a standard deviation or a standard error? Which one of those two do you think you're going to be asked if this was the introductory? Say again?
Standard deviation.
Right. So the standard deviation of the sample, if you take one, would be P1 minus P over N. So it would be 0.3 times 0.7 over 200. And
I don't get it. Why do you do P hat in parentheses after ST, but then use normal P in the square root?
because that's the dumb way that they write it down. It's not my choice. It's basically saying the standard deviation of the sampling distribution and the standard error of the sampling distribution. Yeah, there's a p hat here and there's not even a p hat in the information. I agree with you. I'd probably think, wouldn't that be, notation wise, wouldn't that make more sense to say SD of P? But it isn't, because there's a sample involved, I'm assuming. Somewhere, even if we don't know what it is, because in this case they're taking 200, so it is a sample. Now, when you're doing questions where you are being asked to round things off, say to 2 or 3 decimal places, let's say in this case it happens to be 3 decimal places, don't round off any of the intermediate answers. Only round off the last bit, right? Only round off this bit to 3 or 2 or 5 decimal places. If you round off too early, I know these numbers are nice, but can you imagine they're horrible numbers? you could end up with some rounding off errors. So let's suppose I make up a story then, right? And you didn't know this because I just made it up. But the proportion of Scotsmen who drink too much is 0.35. Right? And so I would like to test if people who live in my part of Scotland are like that. So I'm going to collect a sample. And my sample is going to be 350 people. And in my sample, the number who drank too much was 100. And so 100 divided by 350 is, as you can see, a really ugly decimal. Now let's suppose the question was, we want all our answers when you're finished to 3 decimal places. Have you noticed that I didn't write this guy down to 3 decimal places? Do you notice I wrote 5? Always do a couple more for spare, right? You don't need to write 10 down, but a couple more for sure. Now, I'm going to ask you to find 2 different guys so that we can get practice, me as well, on which one is which, right? So it's underneath here and it's hidden. And I'm going to put the formula down and it's going to be identical for a little while. Now, which one of these 2 do I use 0.35, the P? And which one of these 2 do I use that ugly decimal P hat? It is under here. Anybody tell me which one uses P? Top one, bottom one. Standard error or standard deviation of the sample?
Standard
Deviation.
standard deviation.
Oops.
Oh.
Well, I've called them both standard error. I'm going to have to change the name of them in a minute, right? But which one of them uses the P? You says standard deviation. You are correct. The bottom one. And won't the standard error one use the P hat guy? Right? So if the question was, what is the standard deviation of P hat? So if the question said that, wouldn't you use this, meaning 0.35? And if the question says standard error of P hat, right, wouldn't you use this? Right. So in this case, it's a 0.35, a 0.65 over 350. And can't remember, to 2 decimal places, let's say.
0.03.
Oh, thank you. Is it like 312 or 298?
0.02549.
Perfect. Yep, 0.03 is. Now, if you do this second one, it's going to be 0.28571 times 0.71429. That's what you get when you take this guy away from 1. It's also divided by 350. And because these are slightly different numbers, I may get a slightly different answer. I may, by coincidence, get the same answer because it is rounded off quite crudely. 0.28571 times 0.71429, all divided by 350. And the answer I'm looking at, would you agree that that rounds off actually on the downside, on the 0.2 side? But it wasn't a lot of difference, right? If you went to 3 decimal places, wouldn't they be much closer to each other, right? Which is kind of what you'd expect. Right, same kind of formula with the same kind of numbers, right? You'd expect same kind of answer. Now, if you were being asked what the mean of that guy is, wouldn't the answer be 0.35? And if you asked what the mean of this guy is, wouldn't you be using the p hat? So isn't the mean just the value of P or P hat, depending on which question you're dealing with? Okay, let's go back to, hopefully the noise isn't bugging you, but it does distract me, as you know I'm easily distracted. So question 5 then, a random sample of 300 adults was taken. 186 of them say they believe in love at first sight. So that's 186 in my case out of 300, which is 0.62. Okay, that's a nice number. It says calculate the value of P hat. Oh, well, I've just done question A. And then it says find the standard error of P hat. Well, I'm getting more used to their naming now. Won't it be that guy? In fact, if they only tell you one guy, isn't it kind of obvious what the formula is going to be? Right. So in this case, it's going to be 62 times a 38 all over 300. And they want it to 3 decimal places, and I get 0.28. Most of the questions now are going to look like this one. You're going to get a sample size, and you're going to get either that given to you as a decimal, or they'll give it to you in the form of 186 people out of 300 said whatever it is they said. And P hat, well, you find what that is as a proportion, and then the standard error, pretty straightforward. So now we're moving on to the last thing that we do with these is we're going to find the approximate, and it's either going to be 68, which I hate, but there is a question that does it, 95, or 99.7 confidence interval. And it's going to be an approximate one because it's not a perfect answer, but it's good. And we are going to use a guy called the empirical rule. Let's remind you what that rule was. If you take the mean and you add and subtract one standard deviation, doesn't that get you a 68% roughly confidence interval? If you take the mean and you add and subtract 2 standard deviations, that gets you a 95% confidence interval. And if you take the mean and you add and subtract 3 standard deviations, that will get you 99.7% confidence interval. And that's called the empirical rule. Can we remember that? You remember the empirical rule? Remember the hill 168, 295, 399.7. Remember that guy? That's him. Now we're just going to adapt how it looks. I'm not changing the formula at all. But the mean is going to be P hat, right? It's going to be our sample. And it's going to be plus or minus 1 standard error. Or it's going to be P hat plus or minus 2 standard errors. Or lastly, P hat plus or minus 3 standard errors. And that will get me, the first one will get me a 68% confidence interval. The second one's going to get me a 95% confidence interval. And the last one is going to get me a 99.7% confidence interval. So these are the guys we're going to use to find an interval, right? A 95, whatever it might be. So let me do a story. I'm interested in my story on the percentage of people who think that they're too short, right? They'd like to be taller, right? And I don't know what the answer is. And nobody's going to pay me enough money to ask every American, are you happy with your height or would you like to be taller, right? So I get some money. I get enough money to get a random sample of 360 people. And we asked them, do you want to be taller? And 85 of them said, yes, I would like to be taller than I am. And so 85 divided by 360 comes out as that rather ugly decimal, which is what you kind of expect when you do, right? But let's say to 4 decimal places, right? That's what it looks like. Well, I could just say, based on this data, that my best guess is about 24% of Americans would like to be taller. Would you agree? 23, that rounds off to 24%. But that doesn't give me any kind of idea of how good an estimate is. I mean, couldn't I be miles off or couldn't I be pretty near? Wouldn't it be useful? Which is what this is for. So what I'm going to do is I'm going to find an approximate 95% confidence interval. So to do that, I need to calculate the standard error guy. So I need to find p hat, 1 take away p hat all over n. That's going to be 0.2361. take that away from 1, you get 7639. Okay, I can handle that. All over 360. And square root. Well, let's assume that they want the answer to 2 decimal places, right? I'm still working with a lot more because you should. But at the end, they want 2 decimal places. So let's see what that's. It's this guy times that guy divided by 360. And I get 0.02238 and some other stuff, right? Now you notice that I'm keeping this guy to a lot more accuracy than 2 decimal places. I do not round this guy off to 0.02. That's far too early to do this, right? So keep all your in-between working as accurate as you want, right? A couple of more digits, right? 2 or 3 more is always good. Now, a 95% guy, right? According to the empirical rule, isn't that p hat, right, plus or minus 2 standard errors? And p hat is this fella, plus or minus 2 times this guy. So we get this fella plus or minus 0.0. That's 6, that's 7, that's 4, that's 4. So we get this. And then I'll do a take away and an add. So let's see what we've got. 0.2361, take away that guy, which is 0.19134, comma, add these 2 together now. And I get, hopefully I did this right, 0.28086. And now I'll round off to 2 decimal places. There. So I can say that somewhere between 19% and 28%, right? I like percentages. And I have a 95% confidence interval. I am 95% sure that if I did this process lots and lots of times, I'm 95% sure that the right answer is somewhere in that range. And let me emphasize this again. Any number in that range is just as likely to be the entire population answer as any other. This guy, where is he? This guy up here, what? It's about 24% roughly. It's no more or less important than any of the others, right? So 19 is just as likely to happen as 24, the one that did happen. But so is 28 just as likely. But don't you now get an idea of, I'm 95% sure the right answer is in this range? Doesn't that give you a little bit more understanding of what the sample is telling me, right? Imagine I did another version of that story, and I got 21% to 22%, right? And that was a 95% confidence interval. I would only get this very narrow band if my sample size is very large. And if you're interested in what does very large look like, very large looks like 10,000 plus, roughly, right? Now, if I'd got an interval 10% to 35%, right, I could have got that, which is even worse than this. The reason why it's so big isn't that is because my sample is very small, right? And very small is typically 100 or less, right? Now, the one I got was a kind of in-between one, wasn't it? It's about 360, bit in the small side, but, you know, big range. We have a name while I'm at that. What do you call this guy here, the 0.044 thing? 3 letters, mentioned it yesterday. What's his name?
CMO or CMI?
Not sure. It might be part of those letters, but it's 3 words.
Oh, 3 words.
Margin of
Error.
error. MOE, margin of error. Might be the letters you were going at. It's important that when you read about a sample or a survey or whatever, a poll, there's various names for what they're called. It's important that when they tell you something, like 82% of Americans are in favor of insert whatever it is here, right? You know those kind of statements, 84% of Americans. Well, what they've just told you here, right, is that p hat is 84, right? That's what 84% looks like. That on its own means nothing to me, because couldn't it be 84% plus or minus 50%? Couldn't it? And couldn't it also be 84% plus or minus 1%? Shouldn't you know what the margin of error is before you pay too much attention to what the 84% is telling you? Because in this world here, couldn't the answer be 34%? Right? I mean, you can't get more than 100, but that doesn't matter, right? It could be more than that. So always take any data that only gives you a single percentage. Take it with a pinch of salt, right? Don't be skeptical, right? Now, if they then go and they say, and the margin of error is plus or minus 3%, feel better. Okay, that's the answer. Can you imagine politicians? Oh, imagine I'm a really unscrupulous politician, right? I'm really not a very honest guy. Hard to believe that, but Isabella, let's pick something that is totally answerable, and hopefully you will answer. Isabella, do you think Americans should be able to drive cars when they're 14?
No.
No. Next day, big headline. 100% of Americans say no to the 14-year-old travel license. Technically speaking, didn't I tell the truth there? There was one person in my sample, right? Now that's an over exaggeration, but can you see how you can make things seem very plausible by choosing small sample sizes and then not telling anybody how big they were? Margin of error is your way around that. So if I went and said, for instance, do you know the one I went and said about Isabella's answer? Do you know what the answer would have been? 100% plus or minus 100%. So technically, couldn't the answer be 0 or, more than 100, which would be pretty useless. Okay, let's return to a question that they've got. The one I'm looking at on the screen right now is as good as any. And this is a version, question 7. A polling organization does a poll of about 500. It's okay. It's not a great number, but it's okay. And they selected registered voters to estimate the proportion of a larger population who want to vote for candidate Y. Okay, that's a pretty standard question. Although it's not known by the polling organization, P is 0.56. So I don't know how they did that, but evidently they found out that 57% of the people are going to vote for the guy, right? And they take a sample, right? So question A says, give the numerical value of the meaning of the sampling distribution. Well, won't the mean be that guy? Now they then go on and they ask us to calculate the standard deviation. And in this story, the standard deviation, p hat, of the sampling distribution is P1 minus P over N. Right? In other words, it's using that guy. So it's 57, 43, all over 500. And you're just going to trust me that the answer ends up being a whole load of 2s and a 1 to 4 decimal places. And then they ask us to do a 99.7% confidence interval. So in this case, it's going to be P, because I don't have a P hat, plus or minus 2 those guys. So it's going to be 57. Oh, I said 99.7. What should this number be if it's a 99.7 confidence interval?
3.
It's not 2. What should this guy be when you want a 99.7?
3.
Should be 3, yes. So 3 times that guy. And if you go to the interval and round it off, I'm telling you that that's what they got. So what this story is saying is that if you actually did take a sample of 500 people and found out who they were going to vote for, you would get an answer somewhere between 0.5 and 0.64. And so that kind of is evidence, isn't it, that the guy's going to win? Because don't you just need 50% in a person to win? So, yeah. A is about lottery tickets, so I'll skip by that one. Get time for one more. Which one will I do? Let's maybe 2 more. We'll see how 9 goes first. In question 9, suppose medical researchers think that the percentage or the proportion of people, of teenagers that have high blood pressure is 0.7. Oh. Evidently, teenagers have high blood pressure. I would have thought that would have been old folk, but who knows, right? And so they think that they could reduce it, right, if they took calcium supplements. you know, well, when you're a teenager, you really should have, you know, your body's still growing and your brain's still developing, so you should have tons of vitamins. And calcium, I guess, is good as well. So they intend to do a clinical trial, an experiment. So what they did is they got a sample of 330 teenagers, and they got them to take this supplement. And it goes on in question A, and it says, assume that P is equal to 0.7. What would the mean of the sampling distribution be? It would be 0.7. And what would the standard deviation of it be? It would be that guy, right? Which in our case is 0.7 times 0.3 over 330. And so the standard deviation would be, according to them, 0.0252. Okay. It then says create a 99.7% confidence interval. So in our case, it's going to be a P rather than a P hat, but apart from that, it's essentially the same formula. This guy is 0.7, and it's 3 lots of this guy. And to save some time, it's 0.624 when you're finished, and it's as high as 776. So if you gave 330 random high school teenagers calcium supplements, the percentage that had high blood pressure would range just randomly somewhere between here and here. Right? So even if calcium was no effect, right? So it wasn't medicinally helpful, right? Didn't reduce blood pressure. Couldn't you still get a reduction from the 0.7 just by the randomness of your sample? And couldn't you also get a proportion which is much higher than 0.7, again, just by the randomness of the sample, right? Now, they then go on and they say, well, we conducted it and we got 175 out of 330 teenagers. So let's see what that is as a decimal. 175 out of 330. And we actually got the answer 0.53. Okay, 0.53. Now, isn't that what you would expect if calcium had no effect, right? Just randomness. Would you agree that 0.53 is outside of that range? What is that evidence of? Do you think taking calcium actually does reduce high blood pressure rates? Yeah. See, this is what you'd get by randomness. This is what the sample came out as. This is much lower than you would expect by randomness. And if you get something that is outside what you would expect from randomness, then can't you make the next assumption is, okay, it wasn't random. This is actually significant, right? This actually did something. So this is one way you could prove that calcium reduces blood pressure. And then you could, you know, do a little advertising campaign and say to mothers, you know, has your daughter or son getting enough calcium? There's a new, you know, clinical trial out there that has shown that, you know, almost 50% better, right, than it would be if you didn't take it. And then people take it and hopefully it works. Is this p hat a statistic or a parameter? Remember yesterday's names.
Statistic?
Correct. Is this P a statistic or a parameter?
Parameter?
Yeah. Okay. P is a parameter, P is a population, P hat is a statistic, P hat came from a sample. And they actually asked that. and we won't have time for the next one. But what you're beginning to get here is the beginnings of how you prove something in statistics. This is a very miniature version, but haven't I, in a way, proved that taking calcium does reduce high blood pressure in teenagers? Now, if this guy had been 0.69, right, just pretend it was 0.69, isn't 0.69 in the usual range that you'd get from randomness? So that would tell me that taking calcium, I mean, it doesn't hurt you, but it ain't doing any good either, right? Suppose that was 0.87, just for argument's sake. Wouldn't calcium actually be bad for you? Because it would mean that a lot more people have high blood pressure because of it, right? So you can use it to prove something's better. You can also use it to prove something is worse. Okay, last name and bye-bye.